Thank you, Kate, for allowing me to give the talk here today. My name is Heath Mills. I am the CSO for Rhodium Scientific. In my previous life, I was an academic at two different universities holding faculty positions at Texas A&M and University of Houston, which is where I developed a fascination and love for molecular geomicrobiology in extreme environments. And so when given the chance today to talk about immigrating from Earth and the challenges facing humanity with this goal of leaving here and going somewhere else, I obviously went to my home area and went to biology, and so I'm going to give a little bit of a biological perspective on this challenge of immigrating from Earth. And so if we think about having to leave, having to go somewhere, and how are we going to plan for such a long trip? And so you see the child here looking out the window at the moon. Well, when we're talking about immigrating from Earth, we're talking about hopping on a vehicle, hopping on a rocket and going somewhere. Most likely it's through the solar system. I see, there it goes. Through the solar system, and then eventually going out into the cosmos somewhere. So when we're talking about packing for such a long trip, this can be difficult, remarkably difficult, and especially if you pack the way some people that I know pack. You probably pack too much now just to fly even to here. But if we're talking about heading to Proxima Centauri or somewhere else, you may think of packing a cargo ship like this to bring all of your supplies. Well, anybody here that's with NASA, and now I'm doing a lot of work with NASA in the commercial space sector now, packing like this is just not really feasible. So I always like to take a little bit of historical perspective. And when the colonists came over from Europe or from Asia or traveled across the sea, they didn't pack big cargo ships. They packed light. They did bring cargo. They did bring supplies. But they sailed on ships like this, and you don't see them heavily burdened with cargo on deck like that container ship. No, what they planned to do was when they got to the New World, when they got to their destination, they decided to use the resources that they had around them. So they farmed the land. They brought some food with them, but then they raised farm animals. They hunted, they gathered, they used the resources that were around them to even build their structures, their houses. They used the local ingredients even to devise new medicines and learn from those people that were around them and the environment they were in to develop new medicines. The whole point of this is that they used the resources that they had around them as opposed to bringing everything with them. And so now we're talking about immigrating from Earth and the challenges that this would face. And so we're now talking about hopping on a vehicle like this, a ship like this. It doesn't have the sails on it, and I love sailing, but I'll take a ride on this. I don't mind. And if you look at the way the International Space Station is packed, there's not exactly a lot of room for farming in the traditional sense. Now, I put a little asterisk on there because I will talk about growing food. Because the whole point of this is rather than go and bring everything with you, you have to start talking about resource acquisition. And when you start talking about resource acquisition from a biologist standpoint, we talk about and think about total resource accountability. Now, I've also hopped on a lot of sailing vessels and a lot of research vessels. I did a lot of oceanography in my days as a geomicrobiologist, and I'd love to hop into a galley and see a galley that looked like this, that was well stocked, but usually after 4 or 5 days, there wasn't a lot of fresh fruit and vegetables available. And so now we're talking about going much further out. And so instead of resource accountability out of a galley that looks like this, we're talking about resource accountability on a molecular level. Because you need to now start to consider everything that you have brought with you on this voyage, on this trip, on this immigration from Earth at a molecular level, and you must account for everything. And so this is where this whole biomanufacturing starts coming in, because now we have to grasp in our hands and be able to mold in our capacity every molecule that we bring with us, everything that we need, because ultimately we are in this vessel. We are in this bottle. We are contained within a ship, everything from Earth that we need. And so we must keep this cork on this bottle. We must keep this cork on this vessel. We must account for everything when we go out and start venturing out into the stars. And so that's where my title came in with this no trash idea, which boils down to no waste. We must identify how to recapture everything that we bring with us when we go out in this area, because if you start to lose something, if you start to produce waste, well, now you've just produced a rate limiting factor into this whole equation. You have built an end process for your mission. You cannot go any further because now you have run out of something that you drastically needed. So this is where resource flexibility has to come into play, because on this mission, on this vessel, on this expedition away from Earth, you have to take everything that these original colonists came over and decided to do and decided to utilize here and put it into onboard manufacturing. You must be able to produce what you need on the ship that you are now traveling on. And that becomes the challenge, because in the end, the key terminology here is the recapturing and repurposing of everything that you've brought with you. If something gets locked away as waste, if something gets locked away as trash, you're in a lot of trouble. Because you can't just run down to the store, you can't call Amazon, not yet, maybe a little bit, but you can't call Amazon and have it delivered to you. So, you must be able to do this. So, our perspective on what we're doing right now at Rhodium Scientific is that we are working with industry, academia, government labs to start doing and working with some research and supporting biotech and life science research on the International Space Station, which for me, growing up as a NASA junkie and even doing space camp and everything, I've enjoyed getting to understand more of what is going on the International Space Station. There's hundreds of systems on board. Being near Johnson Space Center, we get to hang out with a lot of the engineers and everybody that's working on these systems, so we get to hear a little insight into them. And so I'm going to talk about 3 of the systems right now, because these are ones that we're actively working with new research and developing some new things on. And that's with the CO2 recapture system, some of the resupply vehicles, and the waste, because if you can't give a space talk to a general crowd without somebody asking you, how does the astronaut go to the bathroom? So I might as well throw a slide up about it. So with that, water recycling, and we know some of the teams that are involved in this, water recycling and water recapture is doing fairly well on station. But there is a solid waste issue that literally is going down the drains. And so that's carbon. That's a usable resource. You may not like to think of it, but it is a usable resource. And so right now, with some of the research partners that we're working with, some of the teams that we're working with right now, we are working on some ways of repurposing waste. And so we're doing this with some engineered microbiology, engineered bacteria, and I'm a microbiologist and I won't go into the full details on this, but through some engineering, some genetic engineering, we're taking human waste products and producing plastics. All right, now you can use those to build structures, you can use those to build containers, you can use those to do 3D bioprinting, 3D printing. Also, as a pharmaceutical, using waste materials to produce pharmaceuticals on demand. Also, biofuels. You need fuel on this ship. You need fuel to power some of the different resources on board. So we're now converting, recapturing, repurposing that carbon that was now considered waste into a usable product to be able to maintain the longevity of this mission. CO2 is also a fun one. Right now on station, CO2 is scrubbed out. These filters have to be changed out. The filters are now trashed, brought back down on one of the vehicles, Cygnus, or brought down mostly on Cygnus, and burned up. That's carbon. That's oxygen. These are molecules that you need to recapture, because if you start running out of these, you don't have a resupply mission. So what we're working on right now is some algae-based and some cyanobacterial-based processes with a handful of different teams to transform that CO2, to recapture that CO2 back into an organic system, to close that carbon loop, and so that now you can take that CO2 and produce pharmaceuticals and nutraceuticals, things that the crew would need during such a long mission. Obviously, then you can also eat this. So now that CO2 that was expelled now becomes back into the biomass, and you can now reconsume it. You're not losing it on a filter, you're reusing it back into the biological systems. And then also there is another biofuel component to this because, I mean, also we are coming from Texas, so we have to talk about fuel all the time and energy, and that's just obligation coming from Texas. But there are biofuel potentials with these as well. And another good one here is with reprogrammability. Now, the colonists that came over, they didn't know all the trials and tribulations they were going to face when they got here. They had to be creative. Well, we may think we have a good mission understanding as to what it's going to be like as we're traveling from point A to point B, but what if we forgot about something? Having the capacity through working with several different teams right now for synthetic biology and also GMOs, which are genetically modified organisms. Everybody hates them in their cereal, but you know they're going to be good on the mission. But having something that you can reprogram on demand to satisfy those needs, now you start developing drug delivery systems. We're working with a group right now that you'll hear from her later about a drug delivery system. Also, gut microbe additives. So now you may be nutrient deplete in some certain amino acid or some certain vitamin. Well, what if your gut microbiota can produce it for you now? Well, that's not a bad way of taking a supplement. Take one now and you're good for 6 months as opposed to taking 2 and calling me in the morning. And then also even with an information repository, because as you go on these long missions, as we've heard with evolutionary pressure, systems evolve over time. Well, what if you want to maintain a certain understanding and a certain capability within a biological system? Well, you can preserve some of this, and as you need it, you can bring it back out in an engineered system and now get that on-demand resource that you were looking for. And so this is one thing that we like to do, and we like to think about testing some of this now. Don't wait until we're ready to go to Proxima or wherever. You want to be able to test this now. And so we are looking at and helping groups right now do some on-orbit testing, because when you get into microgravity, one thing that is common is that life changes. Life changes in a microgravity, low-dose radiation environment, life changes. Some things grow faster. Some metabolic rates increase when they get to microgravity. So now you have to constrain your experiments with this new principle and this new understanding of how the microbes respond to this new environment. Some other areas and some problems now is that some pathogens on orbit that are on Earth, Earth-based pathogens, become less pathogenic on orbit. Some become more pathogenic. So you might want to test the organism before you go off on a long mission, and all of a sudden you've created something that's a microgravity superbug. So testing those out, NIH also loves this a lot, and some other pharmaceutical companies like this a lot, because this is also terrestrial drug discovery too. If you can find out why a pathogen turns off or gets worse in orbit, there's also drug discovery involved in this. So on-orbit testing can change things. And also, because we're close to Silicon Valley, I had to put up the word hacking. At some point, you can growth hack. You can hack biological systems by understanding how life changes in these microgravity environments. It's like understanding that temperature changes how biology works on Earth. Gravity changes the way biology responds to their environment. And so if you can understand how something grows faster up there, maybe you can re-engineer it on Earth to grow faster and more efficient here. So there's reasons to go and do this, not just because we're going out to Proxima Centauri or wherever else, but because we're also living here. And so the results from testing on orbit now can also help life on Earth today. And that's one big thing that we like to do at Rhodium Scientific, is that we're wanting to utilize our resources and those discoveries that we're finding on orbit to help all of life on Earth. And so with my last few seconds before Kate comes and tackles me, I will say that Rhodium Scientific, and this is our background here, and our CEO, Olivia Holzhaus, is here with us, and also talk about RP will be up here for the panel. But our company is involved with helping groups get to orbit and get to and start testing some of their experiments. And actually, with this group having amazing ideas and great ideas, we like to go forward and actually start working on some of these projects with you. Not just come up with good ideas, but let's go test it. We're in my lab, I was always an experimental guy. I did a little bit of theory, but a lot more experimentation. And so this is where we like to go and actually start doing some of this testing. And so we are actively seeking new projects, new ideas, With commercial space side, we are going to orbit much quicker. We're going to orbit and completing projects in less than a year. So let's test some of these ideas that we've talked about over these past 2 days and see what we can come up with and get ready for this trip off of Earth, immigrating off, but also help life here on Earth. And with that, I'd like to thank you guys and thank Kate for giving me the chance to do this today. And our email addresses are on the board now. And if you have any questions after this meeting, I'm glad to answer them on email and glad to take your questions now. Thank you.
So what's some examples of microorganisms that actually are differently pathogenic in space, and why is that? What's actually going on there biologically?
Two good examples. Staph aureus. Staph aureus, it's been shown in a group that we worked with, and a PI that we worked with Staph aureus, that staph is no longer pathogenic in orbit. Staph is a common skin pathogen. 30% of the population carries it naturally. You get up to orbit, and there is a central metabolic shunt that happens within Staph aureus that even turns off the gold color, aureus gold. It's no longer gold. It's also no longer pathogenic. Why is that? Great question. There's a pharmaceutical line there. Salmonella, Cheryl Nickerson, ASU, did a lot of work showing that salmonella is actually more pathogenic when it gets to orbit. The trick now is, and what we're focused on now is that we're finding a lot of really cool nuggets of information and findings on orbit, going back and constraining some of these experiments with better controls, with better replicates, with a better industry standard operating procedure to get better quality assurance on some of these flights. Now you can start getting into the molecular, why is that happening? And that's something that we really are enjoying doing right now, is getting into those. So the complete answer is TBD, but that's two good examples. Okay.
So thanks, yeah, very interesting. If you look at the way that we grow things, whether it's plants or people, we don't bring trees in and plant them. We plant the seeds of trees typically, and we don't bring people in and we grow them. And won't go there. But anyway, part of so the question really is the concept of going even beyond the seed level of actually making the seed in process. So have you had any thoughts of how one makes a biological system from, the proton, electron level on up, rather than bring even the DNA with you, but actually starting from a way to actually fabricate the actual DNA itself or whatever is necessary?
It's a very good point, and that's actually the reason why I framed those 3 different slides in the order that I framed them in, because the last one was focused on the reprogrammability and the synthetic cells and the GMOs, because that allows you to start building not just for a product, but for a biological machinery based upon what you need. And so hearing a lot of the talks today and yesterday, and also with the synthetic biology crowd, I think this is where we are going, is to having the capacity to build biological machines, take advantage of what biology already does well, which we talked about earlier about 20-minute replication in microbial systems. These are small engineered vessels that replicate very fast and are also very programmable. And so if you start going down to the molecular level of these, can we start to now construct these little engineered vesicles to do what we want, and how programmable can we actually make it, and how on demand can we make it? You can see a trend through the field leading to that, and I think that will make a lot of what I was talking about even easier, because now you can just build it from literally the ground up. No pun intended on that. But. Questions? Oh, thank you all very much.